The robot used in this experiment is the Pioneer 3DX, a differential drive mobile robot, which is DDMR for short. It is equipped with two independently controlled wheels, allowing movement in forward, backwards, and rotational directions by varying the speed of each wheel. The robot's position and orientation are represented by three parameters: X for horizontal position, Y for vertical position, and V for heading angle. The initial condition for the simulation is set at x equal to 0, y equal to 0, and v equal to 0, placing the robot at the origin facing along the positive x-axis. Motion is modeled using a standard kinematic approach, assuming ideal surface conditions without slip or external disturbance. This configuration supports controlled movement and accurate path planning in both open-loop and closed-loop simulations. MATLAB Simulink is used as the main simulation tool for modeling the robot's control system. This software enables visual block-based programming, allowing dynamic systems to be simulated in a clear and organized manner. An advantage of using Simulink is its ability to quickly simulate control behavior and visualize system outputs without requiring physical hardware. The open-loop control system is modeled using a predefined input command without relying on sensor feedback. Its primary advantage is simplicity, making it suitable for demonstrating direct input-output relationships. In contrast, the closed-loop control system includes feedback from the robot's current position to adjust movement toward the target post. This method improves accuracy, and reliability by continuously correcting trajectory errors. However, the MATLAB Simulink has a limitation, which is a limitation is that it assumes ideal condition and may not accurately reflect the real-world variables such as noise, delay, or friction. And for the open-loop control, the main disadvantage is its inability to correct errors or respond to disturbance during motions. And the closed loop, the disadvantage lies in the requirement for careful tuning of proportional gain values, which, if not optimized, can result in slow response or instability.
The setup of the experiment. The block diagram of open loop and closed loop control were opened and downloaded from the link given into the computer, and the software MATLAB was used to conduct the experiment. And for both part A and part B, the desired position, which is x equal to 6 and y will be remain 0, have been selected. And for both part A and part B, the initial condition was preset at x equal to 0, let's y go to equal to the 0, step-by-step v and equal to explanation 0 of the procedure. For the first one, open loop control. The open loop control block diagram was downloaded and opened, and the initial was preset at x equal to 0, y equal to 0, and v equal to 0. The Simulink file was run and the output scope was observed. The desired final position was selected 60, which is x equal to 6 and y equal to 0. The input U was varied such that the robot arrived at the desired position selected in step 4, and the last one, the output graph, was been observed and recorded.
For the step-by-step to do the closed-loop control observation, the given closed-loop control diagram was downloaded and opened, and then the blocks were rearranged to form a feedback connection as shown in the figure from the position mirror to the controller. And then we use the same desired position like we do in the part A and input into the system. For the parameters, which is the proportional gain values, we choose the set 1. The given set 1 is KPU is 1, KPW is 1. And for the set 2, we decide to do the KPU is 1.5 and KPW 0.5. And then for set 3, KPU is 4 and KPW is 2. So we adjust the code to do our decided gain. And then we simulate and the observation was performed and analyzed.
And we are looking at the observation and discussion of each input u. For the first one, input u step time 6 initial value 1, which is the robot regularly increases in position with a steady progression towards the desired position, which is s equal to 6. And the y coordinate remains at 0, showing no deviation, confirming the robot's intended motion is along the x-axis, and the robot's orientation is also remains steady, suggesting no significant turning as the robot moves straight along the x-axis. And we go to the input use step time 5, initial value 2. The x position increased faster than in the previous case, which is reaching the desired position x equal to 6, which is quicker. And again, the y coordinate stays at 0, and the robot's orientation again stays relatively constant, reflecting a straight line path. And we go to the input u, which is the third one, step time 8.5, initial value 0.7, which is the movement is much slower and the robot approaches the desired position x equal to 6, more slower than before. And the y coordinate remains at 0, showing that the robot maintains a straight path along, and the orientation remains constant throughout the movement, confirming a steady and straight motion.
This is the result where the KPU is 1 and KPW is 1. This is the result where the KPU is 1.5 and KPW is 0.5. This is the result when the KPU is 4 and KPW is 2. From the observation, the set 1 showed that the robot successfully reached the desired position, which is set 0. Same goes to the set 2 and set 3, but the movement was relatively slow and smooth. And then the rest time was longer, and then the stability was high. The robot maintained a straight trajectory with control heading adjustment. For the set 2, the robot reached the target more quickly than in set 1. So it showed that the improved forward speed due to higher KPU. The lower KPU reduced the robot's turning responsiveness slightly. And for the set 3, the robot demonstrated a fast and aggressive movement. So it showed that because it reached the desired position in the shortest time. The higher the highest KPW made the robot turn quickly. So and then the system remains stable. Overall, this gains the stress of trajectory smoothness for fast convergence.